In this video, we want to talk about more in terms of how to use the sigma notation, okay, and how to go back and forth from the series to sigma notation and back and forth, okay. So let's just start it from here, okay. So we're going to ask you, can you convert from a sigma expression to a series expression? So here is the series expression, okay, or the sigma expression. Where it's a summation of terms moving from n equals 2 to 5, identified by a function n minus 1 times x to the n minus 2. So again, I think we implied in earlier videos that this just implies taking this value n and replacing it with integer values starting at 2 and moving up to 5, replacing each term. So it's just the expansion is going to look like this, okay? Not that there's excessive computation there, and you should be able to easily see that this funnels down to this. Of course, the 0 as an exponent there means anything to the first power, okay? Which is anything to 0 power, which is 1. So we identify with what is being generated here is in fact just a polynomial is being generated by this series, okay? Let's take a look at another one. Here's an interesting one, okay? The sigma summation from j equaling 1 to 3 of the log base 4 of j over j plus 1, okay? So that means, of course, log base 4 replacing j each time with values starting at 1, moving up to 3. So that would give us 1 over 1 plus 1, 1/2. Log base 4 of 2 over 3, log base 4 of 3 over 4. Now, okay, we should identify with this via properties of logs that can be simplified, and in fact it is. So we know that the sum of the logs is the log of the products. So that allows us to take this expression and write it as a single expression, log base 4 of 1/2 times 2/3 times 3/4. And we get a string of cancellations, 2 with 2, 3 with 3, leaving us with 1 over 4. So we have the log base 4 of 1/4, which we should identify from previous knowledge of logs is -1, okay? Let's move the other way now. Let's move from series expansions to sigma notation. Typically, a question of this form would say, find the closed form sigma notation for this series, okay? 1, 3, 5, 7, 9. Looks like the string of odd integers. Yes, it is, but more specifically, it is an arithmetic series, okay? And hopefully you recognize that. Identifying that the particular ingredients for the arithmetic series is the first term a and the common difference, which is 2, okay? So recognizing how we find the nth term for our series is going to prove pivotal for us writing the sigma notation. So we should agree that this is the nth term of the nth term of any arithmetic sequence, okay? The nth term is the first term plus n minus 1 times the common difference. With what we found previously, the first term 1, common difference 2, we should agree that our nth term more specifically can be expressed here. As I said, identifying the nth term will help us build the sigma notation, and loosely, the nth term is defining the function that is part of the sigma notation, okay? Now, however, there is a little bit of change in terminology, no big deal. N is usually reserved for the nth term, which is going to be placed at the upper side of the sigma notation, and K is the counter that starts us off at the bottom. So that being said, it's better for us to have our function notation in terms of the variable, which is our counter variable, which of course we list at the bottom of our sigma notation, and the upper limit of the sigma notation being n whether that's going to be a numeric value or not, can be changed from problem to problem, okay? So that being stated, we would say that for this group of numbers, okay, the appropriate sigma notation for that set of numbers would be the summation of terms starting with k equals 1 to 5, defined by the function 1 plus 2 times the quantity of k minus 1. Okay, and of course we could simplify that by, algebraically, distributing the two and combining our like terms and find that it would get us the same thing. Okay, let's try another one. Okay, so here's another series expansion, 1/2, -1/4, 1/8. I trust you to identify that as geometric. Okay. And more specifically, okay, I trust that you recognize that as alternating, okay? And the alternating in the geometric series is merely defined, again, as in any geometric series, by finding the R value by taking the ratio of one term with its previous term. So that being the case, 1/8 divided by -1/4, of course, would give us -1/2. Okay, -1/16 divided by +1/8 would give us -1/2. So we identify that that the R value is -1/2. Okay. Now, so then we should easily identify with any and all geometric series that the nth term takes on the form a times r to the n minus 1. Well, again, a is the first term, and r is that common ratio, and n is the term in question we're trying to find. So applying that to our specific set of values that we found for a and r up here would give us this expression for the nth term of this alternating geometric series, okay? And which, again, as we saw previously, would help to define the sigma function that we would use in our format. This specifically went up to 7. That is, we're generating 1, 2, 3, 4, 5, 6, 7. We're asking for the 7th term, okay? And you should agree that the appropriate sigma notation for this geometric series would be expressed with this notation. You can and maybe should generate those terms via this notation to see if they come back, okay? But I think you can trust that they will. So there again, if we're asked to find that summation, then we know the summation form for geometric series is taking on this form. The summation of n terms, it should be n, not 5 necessarily, is a r to the n minus 1 over r minus 1. And we've identified here that a was 1/2 and that r was -1/2. So I stand corrected here. This should be -1/2 here. Okay. That will be corrected, but you will see, okay, in effect, right down here, it's not going to make a whole lot of difference. Again, I will come back and correct that, but no, right now it should say an R value of -1/2, and that being the case, all things being the same, we just divide the 1/2 by the -3/2. We rearrange this. This will effectively come down to say plus. Nonetheless, okay, this quantity is going to be minuscule, very minuscule, and in the long run, summing up these 7 terms will approximate 1/3. And you should try to illustrate for yourself that the summation of infinite terms using that form that we have for geometric series would actually sum that up to exactly, okay, 1/3, okay? Again, my apologies, this will be corrected. You should correct it for yourself, okay? This R value should be -1/2, okay? I will make the changes on the PowerPoint demonstration for yourself, okay? So that's it for this round, okay? Hope you appreciate it.